All right, ladies and gentlemen, this next concept of differentials is huge. The concept is overwhelmingly huge and makes a massively huge impact. The solving of these is incredibly easy. The concept is whopper huge, but the application that goes with it is super easy. We know that we find a derivative. One way to write derivative is dy dx, right? We already know that. So this is equal to f prime of x. That's equal to my derivative. So if I multiply both sides by this dx, dy is equal to f prime of x dx. This is what I'm talking about with a differential. Instead of writing the dy dx on the left side, I'm just going to write dy over here, and then your differential is putting this dx afterwards. Now here's what this means. This means that I am taking the derivative with respect to x. That's what that means. I am taking that derivative with respect to x. This is an x, and I have x in my problem. If I have something like dy is equal to f prime of, w, then my differential has to be a dw. See what's going on here? So that y just means function over here, right? Y equals situation. So the derivative of my function, y is that variable. This w has to relate to my differential w because that's what it is. This concept will take us into integration. That's what makes it such a big concept. All right? Your variable has to match your differential. Now, I'm going to harp on that when we get to integrals. This is just setting that stage. What if I have f prime of r? What would my differential be? dr, right? Because the variable has to match up. That's the whole point. It's not a difficult concept, but it's an important one, because when we start changing up variables within the problem and having multiple integration, that will make more of an impact. All right, a differential, the concept of a differential is off the charts huge. All right, use differentials. It's kind of small in terms of how your book addresses it, but you apply it so much as we move forward that it really makes that difference. So dy is equal to f prime of x dx. Applying these differentials, we're going to use these differentials. So here's number 4.6.60. If I have f of x is equal to sine squared x. So I'm given just a regular function, but I'm going to take the derivative and then put this dx at the end, right? So dy here is equal to, and this is a chain rule, bring the 2 in front, keep the guts of sine, multiply by the derivative of the inside, and we know the derivative of sine is cosine. And then you put the dx on the end because x matches my variables. All right? In order to get credit for these problems, you have to have a dy and you have to have a dx. That is what you do when you find a differential. All right? If you don't have those components, then it's not going to work. So you just take the derivative like normal, right? This is obviously chain rule. Bring the 2 in front. Multiply by the derivative of the inside, you're good to go. All right, let's do another one. Let's have about something like this, because why not? Here's example, smiley face, because we're making it up. Oh, y is equal to, let's just do some polynomial. 7x cubed plus 12x squared minus x plus 3. Use a differential. So dy, yep. And if this were a different variable, let's call this, actually, let's change this, and let's call this p, right? So dp now is equal to a 21x squared plus 24x minus 1, but because the x is the variable, I have this x that goes with my x's, and I have the p that goes with the p. Literally, it's just knowing how do I use my variables. That's what we want to go for here. All right. I think all your problems have dy dx in them. I think they got real basic on that. But I do want to make sure that you know this differential matches the variable in my problem. This up front part over here matches with whichever variable I'm setting it up with. All right. They're not so bad. But notation, 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 that is a big deal in math. Okay, go have fun with this stuff.